Okay, so this chapter has a few major focuses. We start off by looking at one particular distribution, the normal distribution, which is very important in statistics. And then we kind of move on to general sampling theory. And we begin to think why the normal distribution is important, even if our original data are not normal. So that will be kind of next Tuesday. We'll also talk a little bit about probability. But for today, we're going to focus on the normal distribution. So what is the normal distribution? Let's just snip this. So the normal distribution, a Gaussian distribution, let me just draw something here. We'll have the mean in the middle here. It's going to be symmetric. So you can see it's symmetric. If I could draw better, it would be symmetric, i.e. one side mirrors the other. It's unimodal. And it's often, these other names for it is bell-shaped distribution. Or, after the founder, the Gaussian distribution. And basically, it's a probability distribution. And the total area, so the area is the probability. And if you kind of go across, across all possible values of x, I promised you no calculus, but that's just saying the whole area is 1, so the total probability is 1. I can promise you no integral signs on the exams. I don't think the homework's either. So let's kind of move on to the function. And what I want to do is I want to actually take a snippet of that. So let's just take another snippet. And we don't, again, the derivation of this actually comes from polar coordinates of probability functions. We're not going to do anything like that. But let's just draw our normal distribution again. And you could just think a little bit about, about some of these kind of factors on the density function here. The mean is in the center. And we're kind of, when we're looking at the function, the maximum of this is basically when your x is equal to the mu. Okay, we won't go into the maths, but the maximum value of the distribution is at the mu point. And the sigma kind of, as the sigma increases, then also the distribution becomes wider. And as I said on the previous slide, the area here with all the probability in is going to be equal to 1. Okay, so the next little slide, and I kind of gave this example, and I actually drew this in R with some sample normal distributions, is again, let's get rid of that one, and let's do another snipping. Okay, so we have 3 professors teaching a statistics class. So we have, okay, 3 professors. We have Professor Hardass, which has, and this person has a mean of 60 and a standard deviation of 15. So this is this person here, like gives grades all over the place, grading like they're in the 1960s or 70s with an average of 60. Professor Normal, with a mean of 80 and a standard deviation of 10. And then we also have Professor Hardass. No, sorry, we already had Professor Hardass. Professor Suckup, who just loves his students or her students, and we've got a mean of 90. So pretty much nearly everybody gets in the 90s. So these three teachers here have very different distributions of grades. Now, given a cutoff at 100, it's unlikely you would have a completely normal distribution here. But this I think, is a good example of three different kind of normal distributions on the same scale. And here's an example from one of the books, again, just showing three different normal distributions on one scale. Now, what we can do is we can actually create what we call a standard normal distribution. And this is a normal distribution with a mean of 0 and a sigma of 1. So let's just say we have my original distribution. And we have a mean of u. So the mean is in the mu. And we have a standard deviation of sigma. And we want to transfer it to this distribution where the mean is 0 and the standard deviation is 1. Okay, you get that. And interesting, one of the reasons why this is done is to make things easier. So everything's done on a standard scale. Statistics was developed before computers. Now, with computers, we can work out where things are in statistical tables for pretty much any distribution with any sort of parameters. But here, if you put everything into a standard distribution, then if you look at the back of your textbook, you'll see tables of values for that standard distribution. So let's do, okay, so we have some value here. So some value in my distribution. It could be below or above mu. I'll put it below, but it doesn't really matter. We're called x. Where is x on this new distribution? And in fact, this x in this new distribution is going to be called z, because it's a value on the standard distribution, which we call a z. And we're going to say z. We might as well start off with x. But here the center of distribution is mu. We want it to be 0. To make it 0, we can just subtract the mu. And here, the width of the distribution, basically we want something with a width of 1, but we have a width of sigma, kind of, relative to the width. So let's just divide it by the sigma with our width variable here. Just going to tell you, the width sigma is not the width of the whole distribution, but it defines kind of the variance and how wide the distribution is. So if we do our z equals x minus mu over sigma, this x has now been transposed to a z on a distribution with a mean of a 0 and a standard deviation of 1 rather than the original sigma. Original and standard. Okay, and this leads us to the idea of this standard score, which we call a z-score. And basically, I just kind of showed you the mechanics, but it's basically a standard value with respect to other scores. And okay, so after that little COVID cough break, yeah, where was I? I was talking about the standard values. The idea, there's ideas on the standard scores. It enables us to put everything into these standard distributions, which we know a lot of information about, and it also allows us to see where our observations fall on a standard scale. So let me just kind of give you another little example. So let's go through to the next slide. And again, I'm going to take a snip and sketch. I'll get rid of some of these old ones. So you can see here we have our standard distribution, and in our standard normal distribution, we have, around just under 70%, 68% between -1 and 1 standard deviation. If we go between -2 and 2, then this actually goes up to about 95%. And then we go to 3 standard deviations, and it becomes over 99%. So those are some kind of ideas about the, how much of the data of a normal distribution is included between certain levels of standard deviation. And in fact, if you've heard of the Six Sigma approach in quality engineering, the idea is that encompasses all 6 of these sigmas, and it means we need to be able to control about 99% of processes. That's where the Six Sigma comes from. It comes from this idea of standardized scores and the normal distribution. Okay, so let's just consider, we might as well stick with statistics exam. So we'll have a statistics exam. Where we have a mean of 70 and a standard deviation of 10. So if we say, for example, scored a 50, so if my x is 50, then my z is going to be x minus mu over 10. So that's going to be -2. If my x equals 60, then my z is going to be 60 minus 70 all over 10 equals -1. If my x is 70, now this should be self-explanatory, my z is going to be 70 minus 70 all over 10 equals 0. And then if my x is 80, my z is 80 minus 70 all over 10 equals 1. And if my x is 90, I think you can work out that my z is going to be equal to 2, 90 minus 70 over 20. So that's kind of a quick example of, how normal distributions are relative to real data in this context. So let's get rid of this snip. And what we can do is we can relate certain z-scores to certain probabilities. So we can work out if we have a z-score, say we have a z-score of 1, we can know that there's basically this amount of probability less than the z-score, and this amount of probability which is going to be more than the z-score. So here, we won't actually do it from this little diagram. We also have a diagram from another statistics textbook I take. This one's a little bit weird in that it gives the z, it gives the area between the central of the distribution and the z. So if we look at the z, we have 1, 1.01, and then the minor increments on the right, so 1.00 go down, and we can see that this area here is 0.3413. So here we go. This area here is 0.3413. You can see here we've got this here. And you can see here, now we know that this is a symmetrical distribution and we know the total area is 1. So we have 0.5 here and 0.5 here. So this area here to the right of the z is going to be 0.5 minus 0.3413. Which is going to be equal to a 7, an 8, a 5, and a 1. So we have 0.1587 to the right of this distribution. Okay, so let's just say for a z-score of 1, we have 0.3413 between the 0 and this distribution. Now, you could actually point out that we've got 0.5 to the left, so we'd have 0.8413 completely to the left and 0.1587 completely to the right. All of z is 1.0. Okay, so we could actually do this with the table that we have in the back of our textbook, which I think would be a good thing. So let me just get that out. I'll just stop the thing. Okay, so this is your actual textbook. This is what you'll get in your statistical tables. Obviously, because the textbook is actually in my office, but I did have a copy of the tables. So here we are. The z, basically, it gives you two figures. It gives you between the center of the distribution and the z, and it also gives you the beyond the z. So let's go down to z equals 1. And we can see that the mean to the z is 0.3413 as before, but we don't have to calculate the 0.1587 because it's automatically given to us, which is quite nice. Okay, so as this is all a bit kind of abstract, so let's kind of do some actual, example calculations. Okay, so let's just go and go to a whiteboard. Okay, so let's just go through a few example questions. So Q1, we're going to let X be our rate of return. That's the wrong time to ask that question, Microsoft. Okay. So let X be a rate of return with a mean kind of return of 28%. So if you invested in this, you would be incredibly rich, and a standard deviation of 3. In fact, if I had access to this, I would not be teaching this class. I would be on a beach somewhere. So we want to know, and this is going to be, let's just say, an annual rate of return. So let's determine the probability. We ask, what is the probability that the return exceeds 34? So we're going to do probability x is greater than 34. We could also say that this is equal to the probability that z is greater. And how do we convert it to the z? Well, it's going to be greater than 34, basically x minus mu all over sigma, which is 34 minus 28 all over 3, which is equal to 2. Sorry. So we want the probability that z is greater than 2, which is, let's just draw, I always try and draw the little normal distribution. So we're assuming that this is normal. So we're going to have z. Here is going to be 2. So we want the area basically to the right of the z. You know, what's the area where the z is greater than 2? So let's have a look at our z value here in our table. And we can see to the left is 0.4772. And if you can look very closely, that's 0.0228. So that's the area to the right of the z from the table. So it's pretty small. You know, a return of 34% with 2 standard deviations above the mean is quite a small return. So let's do a second one. So we've got a particular, maybe we are like building something that's very fiddly, I don't know. But we have a particular, we require a job requires candidates to score over 80 on a dexterity test. And so we're going to say x is normally distributed. So the random variable, you know, this x candidate scores are normally distributed and there's a mean of 70, 5, and the standard deviation of 7.5. We could actually write like this. We'd say x squiggle, n, and 75. Oh, let's just move up a little bit. comma, 7.5. If we write distributions like that, the normal, it's got the mean and the standard deviation. But let's just write it out longhand. X-scores normally distributed, mean of 75, and just make sure we know there's a dot there. Same here. Okay, so we're given two questions. So, if the job requires, what proportion of the candidates Okay, let's just do it directly. So we'll say if X is going to be 80, then Z equals 80 minus the mean, 75, all over sigma, 7.5, which is equal to 5 over 75. We'll just put it as a fraction at the moment, 2 over 3, or 0.6 reoccurring. And we want kind of greater than this, so we want the probability that X is greater than 80 is the probability that Z is greater than 2 over 3, or 0.6666666. Let's just have a look what happens in the table. So let's just have a look at 0.66 is 0. Where we are, 0.2546, and 0.67 is 0.251. So 0.251 and 0.255. We're going to say about 0.253 in the middle. Important things for exams. Let me just snip this. Let me just see if I can zoom that a little bit. Oh. So important things for exams. If you have a situation like this, so I've got 0.6666, it's not a normal number. And I'm going to have to guess. I'm going to do it with Excel in a second, but I'm going to have to guess what this is. Is it between 0.255, almost just below 5, just above 1? I'm going to say 0.253. In an exam, I'll give anything. If you use either of these numbers or you have some guess between these numbers, it would be a correct answer. So this is like the bound for the correct answer. Just a quick note going forward for the exams. Okay, so 0.253 is our guess. And then B, second little question, is one candidate's score is at 98th percentile. What is the score? Okay, so this is a little bit tricky. So let's just draw this here. So first, let's find the Z. And then we'd use that to find the X. And we want the Z where this area is going to be 98%. So this is going to be 0.02. And this area here is, these both add up to 0.5, so it's going to be 0.48. So let's kind of go back to our thing. And so we want the beyond z to be 0.02. So we go down, and here we go. It's going to be between a z of 2.05 and a z of 2.06. So let's just say, for example, we're going to guess this z as 2.054. So you see here, again, it's a little bit closer, 0.202 and 0.197. So it's a little bit closer to 205 and 206. So we're going to guess that our z is 0.054. Because it's almost, you see, it's almost equidistant, but a little bit closer to the above one. So let's just say the z and we've got, remember we had z equals x minus mu all over sigma. So we could actually just rearrange that and we could say x minus mu equals z sigma. And therefore x equals z sigma plus mu, which in this case is going to be 2.054 times 70.5 plus 75, and that score is going to be 90.405. So we'll say this is the score at the 98th percentile. Okay, that's using it with tables at the back of the book, but we can actually, let's go back all the way to our first example. No, we don't want to remove that. Q1. And you see here we had z greater or equal to 2, and we looked at the table. Now let's go to Microsoft Excel. Let's just do an equals. And we've got a function here called norm dot dist, and we also have norm dot s dot dist. We've got norm dot inv and norm dot s dot inv. The norm dot dist and norm dot s dot dist functions, what they do is we pass them a z value and it passes us a probability. So let's just say we go to this first one, we have a z of 2. And what do we get? Oh, we have to put it's cumulative, which is true. We get 0.997725. If we do 1 minus this, we get 0.02275, which to 3 decimal places is 0.0228, which is the answer we got before. Why do we have to do 1 minus? Well, that's because Excel, it always gives, just to confuse you, if you have a z, Excel will always give the area to the left of the z, all the way to the edge of the distribution. It doesn't give between the midpoint and z, it gives everything to the left of the z. So if we're looking for greater than z, then we have to do 1 minus this area. And this is actually more natural when it comes to how probability functions work. You look how, cumulatively, how much area there is up to your certain point, and then we want 1 minus this area, But that's just how Excel and some textbooks work. Okay, so another way of doing it is we could do 1 minus norm.dist, and we don't even have to calculate the z. Okay, that's better. It may equal, so 1 minus norm.zist. And here my x was, if you recall, we're looking for returns greater than 34%. There's a mean of 28 and a standard deviation of 3. And again, we say always have to put true because we're not looking for a point area. We're assuming a cumulative distribution. And again, exactly the same answer. This is the answer that we got before. Next question. So we're looking for x is greater or equal to 80 with a 75 and a mean of 75 and 7.5. And we found that our z was 2 over 3. So let's just do equals norm dot. And my z is going to be 2 over 3, and cumulative is true. And then we have to do 1 minus that. Don't forget, because we're looking to the area to the right. And we get 0.252, almost 252, 253. So we got pretty much the value that we guessed from the book. But this is going to be a little bit more accurate. We were kind of on a boundary there between like 2.53 and 2.52. Okay, and we could do exactly the same as before. So 1 minus norm dot dist. And this time we're going to pass the x, which was 80. We pass the mean is 75, standard deviation is 7.5, and cumulative is true. So we get exactly the same value. And so the final thing to do, remember this question, and this is easy for us now because the 98th percentile, I said Excel just counts the area to the left, 98th percentile, 98% of the area is to the left. So we just have to put like 0.98 into Excel, and we want to know what the x is. So what we could do is now let's just do norm.s.inv and the probability 0.98. And that gets us the z value that we found before. But of course, we have to multiply it by the standard deviation, the sigma, and add the mu as we did. And we get 90.403. So this is just the calculation we did here. But again, with Excel, we could actually do everything automatically. So we could do equals norm.inv. So the probability 0.98. This is a distribution with a mean of 75 and a standard deviation of 7.5. And voila, we got the same answer as the calculation. So I'll make sure that this little sheet is on Excel for you to play around with. I'll just call it class. I think I've called it class examples. So I think it might, if it's not on Canvas, I'll add it. And hopefully that was a good couple of examples to get you thinking about how you can actually make some inference on, real world distributions using the normal distribution.